This is a video about intermolecular forces. You can find this video on SRHS Chem or on YouTube channel LEFFELlabs. So there are two main types of attractions. We have intramolecular forces and intermolecular forces. So intra means within. So these are going to be the attractive forces that are the chemical bonds between atoms within a compound. So intramolecular forces refers to ionic bonding, where we have attractions between cations and anions that have formed due to the transfer of electrons. We have metallic bonds. This is where atoms of a metal will give up electrons, forming this electron C. The cations left behind are mutually attracted to the electron C, and this holds together the atoms of a metal. Last, we have covalent bonding, and this is where atoms are going to share electrons in order to achieve a stable electron configuration. So this is different from ionic in that we don't have any transfer of electrons going on. Instead, we just have sharing, so we don't end up with those charges like we do in an ionic compound. Inter means between. So intermolecular forces refer to the attractions that occur between two or more molecules. So intermolecular forces are the forces between molecules, and in particular we focus on the attractive forces between molecules. These are the forces which hold together substances. So if you have a substance, there's going to be attractions between the molecules of that substance. These forces ultimately dictate the physical properties of substances, such as boiling point, melting point, and surface tension. These properties are all governed by how strongly these attractive forces hold together the molecules in a substance. Intermolecular forces also affect the way that chemicals react. In order to form a chemical bond, the atoms must get close enough so that their electron clouds can overlap and interact with each other. The atoms have to be close enough in order to provide the possibility of a chemical reaction to occur. There are three main types of intermolecular forces which have some differences that are very subtle. It all comes down to charge. If you have a positive charge and a negative charge, there's going to be an attraction between the two. The stronger the positive and negative charges are, the stronger the attraction between them will be. Most molecules are neutral species, so they don't have full positives and full negatives. That would be the world of ionic compounds. Instead, we have partial positive and partial negative. So this isn't +1 or -1. Instead, we symbolize this with the symbol delta. So we have delta positive and delta negative. If you get a large enough distribution of charge, you will have a polar molecule. In a polar molecule, there are two poles, like in a magnet. One side of the molecule will have a partial negative charge. This occurs because one atom is more electronegative than the other, meaning that it attracts electrons to one side of the molecule. This leaves the other side of the molecule very electron poor, giving it a partial positive charge. Such molecules are said to have a permanent dipole. When molecules have a permanent dipole, the charge ends of two different molecules can attract each other. The partial positive of one molecule will be attracted to the partial negative charge of another molecule. This attraction is the intermolecular force known as Dipole-Dipole Interaction. This strong attraction occurs between polar molecules that have a permanent dipole. Now, a subset of dipole-dipole interaction would be hydrogen bonding. So hydrogen bonding is a specific case of dipole-dipole interaction. We call it hydrogen bonding because hydrogen, makes up the partial positive charge, and the partial negative is going to be some highly electronegative atom, such as fluorine, oxygen, or nitrogen. When hydrogen is covalently bound to fluorine, oxygen, or nitrogen, the hydrogen becomes so partial positive and the fluorine or oxygen or nitrogen becomes so partial negative that we get a very strong amount of attraction. So we give this type of dipole-dipole attraction a special name. We call it hydrogen bonding. So two different molecules can attract. Now this is called a hydrogen bond, but that's really a bad name for it because it's not actually a chemical bond. A better name for it would be something like hydrogen attraction. Now at the other end of the attraction scale, at the low end, we have nonpolar molecules. If you have no distribution of charge, then you're going to have a nonpolar molecule. So this can occur for a couple of reasons. First, it could occur because all of the atoms within the molecule have similar electronegativity values, or they may be nonpolar due to the symmetry of the atom. So hydrogen, which is H2, is nonpolar because each hydrogen atom has the same electronegativity. The right hydrogen atom will pool on the shared electrons due to its electronegativity value of 2.1 units. Now at the same time, the other hydrogen, the left hydrogen, has the same electronegativity value. So it's going to pool on those shared electrons as well. It's sort of like an equally matched tug of war where both teams are of equal strength. So there's pooling of those electrons going on in both directions, but since they're both pooling at the same time with the same strength, the electrons are being shared exactly evenly. So this is going to leave a nonpolar molecule. A molecule of carbon tetrachloride looks a little different. It has 4 chlorine atoms with an electronegativity value of 3.0 units and 1 carbon atom with an electronegativity of 2.5 units. So chlorine is going to pool on those shared electrons in that bond, and carbon will also pull back, but chlorine pulls a little harder because it's more electronegative. So this is like an unfair tug of war where we would see that we would have uneven teams. So chlorine is like the stacked side of the tug of war. It's going to pull stronger on those electrons than the carbon would. So this results in what we call a polar bond, which we symbolize with this crossed arrow. So this lets us know that the electrons are being pulled in the direction of the arrow. So we call this bond a polar bond, where chlorine is the partial negative and carbon is the partial positive. However, despite this polar bond, this molecule is nonpolar. At the other end of the molecule, the same tug of war is occurring with another chlorine atom winning. The electrons are being tugged in opposite directions, and each polar bond is canceled out by the polar bond opposite of it. So carbon tetrachloride is going to be nonpolar due to symmetry because all of these polar bonds are pooling in opposite direction. So even though each bond is polar, they nullify each other as far as distribution of charge. Now, even though carbon tetrachloride is nonpolar due to symmetry, there are still going to be attractions between carbon tetrachloride molecules. So if they get close enough together, we will see attractions occurring. Now, carbon tetrachloride is a liquid, so there must be attractions in order to hold these molecules together close enough in order for this to be a liquid. So we call these attractions dispersion forces, which exist in all covalent compounds, even in nonpolar molecules. So this dispersion force is due to temporary dipoles that form within the nonpolar molecule. So unlike a permanent dipole, these temporary dipoles may only exist for fractions of a second at a time. Now, in any chemical bond, the electrons are not stationary. For example, in a chlorine molecule, in Cl2, the electrons are in flux. They're constantly moving around each atom. Now, if you look at the atom at any given second, you might catch it with an unequal distribution of electrons. So this is going to give one side a little tiny partial negative, and the other side will be partial positive because it is electron poor. Now, another nearby molecule could be caught in a similar situation. A weak attraction between the partial positive of one molecule and the partial negative of another molecule will occur as the electrons shift within each molecule. The dipole is only temporary, but the attraction is still there, however weak. So it's a very slight attraction, not nearly as strong as a permanent dipole, but this is the type of attraction that we call dispersion forces. So that's all three major intermolecular forces. The stronger intermolecular force is the hydrogen bond, which only occurs in covalent molecules that contain a hydrogen atom bound to a very electronegative atom, fluorine, chlorine, or nitrogen. Dipole-dipole interactions occur in all polar covalent molecules. So as long as we have that distribution of charge due to different electronegativities, we're going to see dipole-dipole interactions. And last, the weakest would be dispersion forces. So this occurs in all covalent molecules, even if they are nonpolar. Now, these attractive intermolecular forces govern the physical properties of a substance. So in a solid, you have a bunch of atoms that are attracted to each other that are sort of vibrating in place. In a liquid, the particles are able to move a little bit farther from each other, and in a gas, the particles are moving all over the place, very far apart from each other. So as you get less condensed, as we go from solid, liquid to gas, those intermolecular forces are getting weaker. So this is going to affect the properties of the substance. So for example, if you just look at the chemical formula H2O, water should be a gas at room temperature. However, H2O exhibits all three intermolecular forces. So these attractive forces hold together these water molecules together as a liquid. Another example can be looking at the boiling points. So usually the boiling point of a substance increases as the molar mass of the substance increases. So this is the case for H2S, H2SE, H2TE. We see an increase in the boiling point there. But water has an unusually high boiling point, even given the fact that it has such a light molar mass. So it boils way hotter than any of the other examples, and yet it is the lightest of all of those examples. This is because the presence of the intermolecular forces in water are going to hold together those water molecules. So it's going to be making it even harder to separate those molecules and get them far enough from each other that they're able to convert into a gas, which is all that boiling is.